this is the wire, metal wire, through which electrical current is flowing. The diameter of radius of the wire is R. This is the solid metal wire. Say consider this is the copper wire of radius R, through which electrical current is flowing with a density I, electrical conductivity Ke. So now the some of the electrical energy will be lost. Some of the electrical energy will be lost and will be appearing as a heat. As electrical energy is passed through this wire, some of the electrical energy will be lost and it will be appeared as a heat. Because of that, there will be temperature increase in this wire. On the same time, this outside surface of this wire is maintained at temperature T0, and say SE is a heat generated per unit volume. Heat generated per unit volume in this wire, uniform heat generated per unit volume. So, and we have discussed the how the temperature profile will be there for this case. So, so this we observed. We observed for this case the temperature profile will be T minus T0 equals to SE R square by 4K 1 minus R by R square, and flux profile will be QR equals to SE R divided by 2. So most important, okay, among these two profile also, this temperature profile is very important. Temperature profile is the ultimate model equation which you will be getting. Temperature profile means what? So this is the equation which is defining the variation of temperature. So this is my temperature, how it varies with R. So all this SE is given. So uniform heat generation per unit volume. R is the radius of the wire. K is the thermal conductivity of the wire. And here this is the variable. With location at different location, I can get the different value of temperature. This is temperature profile. So this is the most important equation, model equation in heat transfer. If you have temperature profile, so you can do so many calculations. In fact, if you have temperature profile, you can get back this very easily. So differentiate this with respect to R and multiplied by thermal conductivity. So that QR will be equals to minus K dt by dr. Okay, so you will get this equation also from this equation. So this equation is more important. So once you have this, you can get a maximum temperature, average temperature, flux profile, what is the flux at the wall, what is the flux at the center, what is the temperature at the wall, temperature at the center, everything you will get. Using that, you can calculate what is temperature here, what is temperature here, and so on. What is flux here, you can calculate everything. So this equation is very, very important. So observing this equation, so this equation looks similar to what we have seen flow through pipe, velocity profile for flow through pipes. So exactly similar. So that is what I want to just convince you that heat transfer is similar to mass transfer, even though that problem was totally different. Fluid is flowing through a solid pipe. There we were getting velocity profile similar to. Here a current is flowing through. Yeah, 112. Shri Charan.
Sir, by mistakenly I am reconnecting it.
You mute and are you getting everything, Shri Charan? Shri Charan, Mayank.
Sir, I just joined, sir.
Okay. So this is what temperature profile you will get. So maximum temperature will be at the center. Maximum temperature will be at the center. So this maximum temperature will give me idea about what kind of insulating material will be useful for insulating this material such that will withstand a possible maximum temperature. Okay, and everything will get. So in extension of same problem, so we'll extend the analysis. So here again same thing. You can see here everything is same. Consider a electrical wire cross sectional of radius r and electrical conductivity K E through the wire. The I is flowing, transmitted, everything. This is the heat generated, heat production per unit volume. This is I square by Ke, where Ke is related to potential difference. Only the changes is here, where E is a voltage drop over the length. If the air temperature is given, now instead of surface temperature, what is given here? Here this surface temperature was given T0. Now in this, instead of surface temperature, air temperature around non-insulated wire. The air temperature around non-insulated wire is maintained at TAI. So air temperature is given and temperature variation in all other thing is same. This is non-insulated wire. This is non-insulated wire and air temperature is given. Air temperature is given means this is the case. Everything else is same. So here I have a wire which is producing SE energy, but instead of this surface temperature, air temperature is given. So how to handle this now? Can anybody give the input? Air temperature is given.
Convection,
Yeah,
sir.
yeah, very good. So this heat transfer coefficient is also given. So now so this temperature, surface temperature can be correlated with the air temperature using Newton's law of cooling. So in fact, it is not a convection, it is total flux at the wall. Okay, but it is dominated by convection. So H into delta T. So this temperature is correlated with this thing, and hence you can get the temperature profile in terms of air. Can you try for this? Okay, take this problem as a tutorial problem. Whatever both the problem we were discussing today is kind of tutorial problem only. It is the extension of this problem only. So here the temperature was given here T0, and now here actually T air is given. What will be the temperature profile? Just solve for this. Exactly everything else will remain same. You will get the same differential because here temperature is varying only in R direction. Temperature is not varying in L direction. Temperature is not varying in theta direction. Reasons are exactly similar to previous problem. It is not varying in theta direction because problem is symmetric around theta and it is not varying in L direction, neglecting end effects. As temperature is varying only in R direction, so certainly there will be flux only in R direction. So differential thickness will be taken only in R direction. So volume of the differential shell will be twice pi small r into delta r. This will be volume of a differential shell, and surface area of the differential shell will be twice pi small r into L. Now rearranging the equation, multiplying, dividing it by, so you can say twice pi delta r into L and multiplying it by -1 and rearranging the equation. So you will get the same differential equation for flux. Flux profile will be same. Flux profile will be same. Only temperature, because for flux profile you have used logical boundary condition. Till that point everything is same actually. Then temperature profile, while temperature profile, the boundary condition now I cannot use. At R equals to R, temperature is T0. So what will be the boundary condition here actually? Yeah, anybody? What will be the temperature boundary condition use here actually? You can see here.
Hello, sir.
Yeah, tell me.
Yes, a modified boundary condition.
Modified boundary condition, what will be that modified boundary condition? So here, till this point, exactly everything else will be same. Okay. So you will be getting this equation, rearrangement is same, everything is same. This is also logical boundary condition you can use and eliminate C1. Flux profile will be exactly similar. Okay, flux profile will be exactly similar. Only the thing is, after using Fourier law of heat conduction, now here this boundary condition is not available. What is the boundary condition available? Yeah, modified boundary condition. Now flux is given at the surface. Flux can be correlated with this T0 and T air. But here I need a temperature boundary condition. So this boundary condition will not be useful. Instead of that, you will be using, okay, this combination of these two boundary conditions. So temperature is specified at the surface can be estimated by using heat plus normal to the surface, which is given because T air is given and heat transfer coefficient is given. Can you try for this? Okay. So this is what the thing is there. This is previous problem, okay, and this is our problem. So exactly similar thing. Okay, here also exactly similar thing, and this will be same. Okay, this will be same, and second boundary condition will be at solid fluid interface. This temperature is given. Okay, so you try for this. Everybody got? So you need to combine modified no slip boundary condition and surface temperature is given, both the thing. Just a mathematical manipulation, nothing more than that. If anybody is solving, just let me know. If anybody is getting any problem, just let me know. Anybody is trying to solve. Roll number 31. Roll number 31. Roll number 31.
Yes, sir.
So why you are so late in responding?
Sir, connectivity problem, sir.
Okay. Yeah, tell me. Are you solving this problem?
Yes, sir.
So how to go for this? So you will be using Newton's law of cooling. So which will correlate this surface temperature with this air temperature using heat transfer coefficient. Heat transfer coefficient is given, and this flux, using flux at the wall, this will be correlated with the surface temperature, and then you can correlate this air temperature with the you can get the temperature profile in terms of this air temperature. So for this problem, so this is exactly similar. Flux profile will be similar. Only temperature profile is changed. So it will be combination of this modified this boundary condition and this boundary condition. Now assume that surface temperature is T0 only. Okay, surface temperature is T0 and bulk temperature is TB. Instead of TB, it is T air, and this is the flux. Flux is related with the heat transfer coefficient, surface temperature, and bulk temperature. This is Newton's law of cooling. So for our problem, at R equals to R, so integrating this equation, so this integrating this equation and substituting this, so this will be T equals to TR. So this will be this TR, surface temperature. Okay, at R equals to R, what I am getting? I am getting surface temperature. This is my surface temperature. Now I can calculate the flux also at the surface. This is temperature at the surface and this is flux at the surface. And using this, okay, and now this is the flux at the surface. Flux at the surface will be Q R, that will be H TR minus TA, that will be equals to minus K dt by dr at R. So that flux profile you have, or you can differentiate this equation. You can differentiate this equation dt by dr multiplied by minus K. So what you will get? So this will be, and substitute this TR here. So this TR here and dt by dr. So dt by dr is minus SCR divided by 2K. Okay, minus SCR divided by 2K, differentiate. Now substitute it here. Okay, dt by dr at R equals to R. So this is dt by dr and that is estimated at R. So this will be flux at the surface. And substitute it here. Substitute it here. So you will get C2 in terms of air. Okay. So substitute it here and rearrange the equation. Now rearrange the equation after substituting this. So you can get C2 in terms of T air and heat transfer coefficient. Now rearrange this equation and get the value of C2. Everybody is getting this? What I am doing? Because surface temperature is not given, but air temperature is given and heat transfer coefficient is given. So air temperature is related with heat transfer coefficient and surface temperature using Newton's law of cooling. So using this temperature profile, okay, using this temperature profile, I got the surface temperature TR minus SC R square divided by K plus 2 C2. This will be a surface temperature. C2 will be as it is. Constant is not yet estimated. This is surface temperature. And this is Newton's law of cooling. Q equals to H into TR minus TA. This will be surface flux at the surface. Now flux at the surface can be estimated using this equation and Fourier law of heat conduction. This is Fourier law of heat conduction estimated at R. So using this equation, I can get the dt by dr. So dt by dr estimated at surface and multiplied by thermal conductivity will give me a Fourier law using Fourier law flux, and this will be equals to this because this is also flux at the surface. This is also flux at the surface. Okay, now combining this, you can substitute this TR here. You can substitute this dt by dr here. So this is TR. Okay, this is TR surface temperature, and this is QR. This is QR, and this is Newton's law of cooling. Okay, overall this is Newton's law of cooling. This is Fourier law of heat conduction. This is surface temperature. Now using this, I can estimate C2. So what will be C2 equals to? Roll number 34, Dhiren. Roll number 34. Roll number 35.
Hello?
Can you explain what is done on a screen to get the value of C2?
So initially we got temperature profile as T equal to minus SC R square by 4K plus C2. From this we got surface temperature by keeping R equal to capital R, which is minus SC capital R square by 4K plus C2. And we substituted this surface temperature in the Newton's law of cooling, and we equated it to minus K dt by dr at R. Since we know minus dt by dr equal to minus SC R by 2K, and at surface it is minus SC capital R by 2K. And from we substituted both, and now we are trying to find C2 value.
Okay, now C2 is estimated in terms of all known quantity. Okay, and this is Fourier law of heat conduction. This is using Fourier law of heat conduction, flux at the wall. This is using Newton's law of cooling, flux at the wall. So this is also flux at the wall. This is also flux at the wall. Hence it is equated.
Yes, sir.
So what will be C2 equals to? Now rearranging this equation. So this is the rearranging this equation. Just a rearrangement of this equation, nothing more than that. This K is multiplied. Okay. And this is C2. So C2 will be equals to SE capital R divided by 2H plus SC R square divided by 4K plus TAR. Pranit, you got this equation?
Yes, sir.
Anybody else not getting this equation?
Yes, sir. Sir, I have a doubt.
Yes, Shivam, tell me.
Sir, in last slide, we have taken QR equal to minus K by dt by dr at R, right? And we are substituting T as minus SCR square by 4K plus C2. But that T equation is only inside the wire, right?
No, here we are estimating dt by dr at R equals to R. What? You repeat.
The T equation, like dt by dr at R, the T equation we are using minus SCR square by 4K plus C2.
This is true for R equals to 0 to R equals to capital R.
Yes, sir. But we are at Q equal to R, we are considering for R and air, right? At temperature at R and air. So we
Okay.
cannot.
So this is what is this actually? This is flux at the surface.
Yes, sir.
This is flux at the surface. What is this? This is also flux at the surface. So Newton's law of cooling is relating my surface temperature, air temperature, and heat transfer coefficient with a flux at the surface.
Okay. Yes, sir.
This is flux at the surface, no?
Yes, sir.
This is also flux at the surface. You can say R.
Yes, sir.
So this temperature profile is true till R equals to R. That is what I am using. dt by dr. This is dt by dr. This is true only up to R equals to capital R. And this I am taking the value at R equals to R only, not greater than this. Okay, I have substituted this R equals to R and then substituted here.
Yes, sir. Yes, sir.
Okay.
Yes, sir.
So this is kind of using flux profile. Okay, this flux profile is also there. Okay, you can use directly that flux profile and keep R equals to R. You will get same thing. Flux profile is SCR divided by 2. Okay, and keep R equals to capital R.
Yes, sir.
And this is not the only way actually. I am going to explain you some other way also, because you should not think in a very limited manner actually. But now you have equipped with so many subjects actually. You are equipped with mathematics, you are equipped with all manipulations and everything, arithmetic, everything. That logic, all logic you should apply here actually. Now this whatever subject you are studying in third year and final year of chemical engineering are application of whatever knowledge you have got. This is you got some information from heat transfer, mathematics, everything you need to come, and this is not the only way. Okay, you can have any other way also, only but you should not be wrong in logical and substitution. Okay. So everybody is getting this value of C2. Now substituting this in temperature profile, this is my temperature profile. What will be temperature profile? Temperature profile will be this actually minus SCR square by SCR. Rearranging this equation. So T minus TA will be equals to SCR square divided by 4K 1 minus R square by R plus SCR divided by H. So this I will get a temperature profile in terms of air temperature. Everybody is getting this temperature profile. Yeah, roll number 36. Yes.
Yes, sir. Yes,
Did
sir.
you
I have
got
got
this?
the profile.
You got it,
Yes,
na?
sir. Yes, sir.
Now here you can see this is air temperature. Air temperature, but if air temperature is given, I need a heat transfer coefficient also. Okay, air temperature is related with the temperature profile only when heat transfer coefficient is given, because this air temperature and surface temperature is related to each other using heat transfer coefficient only, flux. Okay, so heat transfer coefficient is also, so here this is heat generation per unit volume, this is radius of wire, this is thermal conductivity of wire, this is radius of wire, this is heat generated per unit volume, and this is heat transfer coefficient, and this is radius of wire. So given a value of R, so I can get this temperature, and flux profile will be exactly similar because this is constant, this is not varying with R. So as soon as you differentiate dt by dr multiplied by k, it will be SC divided by 2. So exactly same thing you will be getting. Okay. So as soon as you differentiate this temperature with respect to R and multiplied by minus k, so you will be getting, this is the flux profile, SE small r divided by 2. Okay, SE small r divided by 2. That is what temperature profile you will be getting. Okay. Now this is one way. Another way is there actually. So now what I will do, I will use same, but I will assume that, I will assume first surface temperature is T0. Now as soon as I assume surface temperature equals to T0, this is my temperature profile, this is my flux profile. Both the profile we got it, but here I have C2. Now we need to estimate C2. We need to estimate C2. For estimation of C2, I will assume that surface temperature is T0 first. Okay, so assuming surface temperature is T0 and combine these two boundary condition, and then T0 is related with the air temperature using Newton's law of cooling. So initially I will assume the surface temperature T0, and for that we have already estimated the temperature profile. Okay, this is the temperature profile and this is assumption. Okay, I have assumed some temperature T0 at the surface. Okay, some temperature. Now, but T0 is not given. Air temperature is given. How air temperature is related with the T0? Using Newton's law of cooling. Okay, using Newton's law of cooling. Now I will be using this modified temperature boundary condition or solid fluid boundary condition, where Newton's law of cooling. So QR, okay, Q flux at R will be equals to heat transfer coefficient T0 minus TA. So using this, I can estimate QR, and T0 can be estimated in terms of TA. So this will be QR, flux at R equals to R. So SER divided by 2, SER divided by 2, and this will be substituting it here. So this will be SER divided by 2H. Using this, I can get T0. T0 equals to SER divided by 2H plus TA. Now substituting this T0 here, here. So this is what exactly same temperature I will get. Okay, this is another way. So it is the combination. Initially, I will assume the temperature. Then I will assume this fourth boundary condition, Newton's law of cooling. This is first boundary condition, combination of first boundary condition and fourth boundary condition, to make mathematically easier. So initially I got the temperature profile in terms of this assumed temperature. Now assumed temperature need to be related with the T air. For that I am using flux profile. This is the flux profile estimated. This is Newton's law of cooling. So here T0 is related with the T air and heat transfer coefficient. So heat transfer coefficient. Now substituting it here and rearranging the equation, I will get this temperature profile. You try out this also. Okay, exactly same thing. That is what I am telling, that in mathematics there can be more than one way to solve the problem. Most of the time there will be more than one way. Only the thing is you should be correct in this thing actually. And yesterday I have given you solution for mid-sem exam. Don't think that that is the only way to solve the problem. There can be other way also, and there can be some mistakes also in that solution also. So your assignment is to search for mistakes, search for alternate ways also, and search for whatever possible ways that can be using that. Only one idea was given how to solve the problem. It was very easy actually. First of all, this second problem was very tricky because you cannot solve that integration. You cannot solve that integration x minus 1 upon x raised to 1 upon n. That integration is not at all possible. Hence, that hint was given. Instead, you can write mu effective dv by dr, and assuming, now here you need to assume mu effective constant, otherwise you cannot solve the problem. So problem without solution will be nothing actually. You need to solve the problem. In real life problem also, there will be so many time you will stuck with no solution. So you cannot say that solution is not available. You need to give the solution, add some assumption, add some simplicity, but you need to arrive at some solution. Might be that solution will be slightly away from actual solution because of assumption. And you can write the limitations. So limitation was, so as for n greater than 1, solution is not possible. This solution is possible only for n equals to 1. Similarly, here also, what we have seen is there are two ways, and both ways are same. Even though it looks mathematically different, this way and this way actually. So this is, so this way and this way, both are same. Here also we are doing same thing, there also we are doing same thing. Only putting the thing in mathematical form is different actually. Anybody not getting this? Here roll number 37, Vignesh.
Yes, sir.
Did you got this temperature profile?
Yes, sir.
Did you got it?
Yes, sir. Yes, sir. Got it.
Huh? Have you solved that?
Yes, sir.
Can you show me on camera?
Sir, 1 minute, sir. Owning the video. Sir, is the video visible? Hello, sir.
Not it. Cannot see.
Sir, now.
Ah, I can see. Okay, very good.
Sir, method 1 and method 2, sir.
Very good, very good, very good.
Yes, sir.
So, roll number 37. Now, next
Yes, sir.
problem.
With me.
Okay. Next problem is case number 3 for same problem. Okay. Case number 3 for same problem. So, this is non-insulating. This is insulating actually. So what is there? Same problem is there. Consider an electrical wire of radius r and its insulation with radius AR. A will be greater than 1. A will be greater than 1. So, so some radius is there, radius of insulation AR. Electrical conductivity of wire material is Ke. So again, same amount of heat generated per unit volume. Now, if air temperature around this insulated wire is maintained at TA, the temperature variation in wire is small such that thermal conductivity of wire. So wire thermal conductivity is Kw wire and insulating material is Ki. So overall temperature variation is small so that we can neglect the variation in thermal conductivity of wire and this thermal conductivity of insulating material and thermal conductivity of K, this electrical conductivity Ke. and heat transfer coefficient is H. Derive the temperature profile using shell energy balance approach. Now here, what you need to do? You need to apply a fundamental which we had covered in momentum transfer as well as in previous two cases of heat transfer also. Here roll number 38, Dayanand. So,
Am I audible?
did you got the problem?
Yes, sir.
Okay. So this problem is same thing. Okay, here in this is the copper. Say consider copper wire. So this is copper wire of radius R, and insulation is of radius AR. So insulation is of radius AR. So this is the insulation from R to AR. R to AR is the insulation only. So radius is AR. So this is R and this is AR. So there is a uniform rate of heat generation here. Kw is the thermal conductivity of copper wire material. Okay, wire material.
Yes,
and Ki is a thermal conductivity of this insulating material. And air temperature is given. And I need to estimate the temperature profile. How to solve this problem?
Sir, like previous problem, like T will be equal to like SCR square by 4K plus C2.
Okay.
Can
So that, anyway, this temperature we were talking about. Now there is one more layer. One more layer is there of insulation. So there we were
Yes, sir.
here, and that was directly exposed to air. Now this is not directly exposed to air. This is covered
Sir,
with
we
some
can
insulating material, and this is exposed to air. And thermal conductivity of this wire is Kw, and thermal conductivity of this is Ki. And there is a
we
uniform
could
heat generation only in copper, this wire. There is no heat generation here. Yeah, anybody else in the class?
Hello, sir.
Roll number
40.
40. 40, Ravi, tell me.
Sir, as we related the wire temperature with and the air temperature with Newton's law of cooling, the same thing can be done here. The wire temperature
Here,
and
this wire temperature is not exposed directly to air. No, wire temperature, wire is insulated by this insulation, and that insulation temperature is exposed to air.
sir, wire temperature can be assumed at T naught temperature and
Okay, here you will assume T naught. Then how T naught is related with TA?
T naught will be the related to the temperature on the insulated material with Newton's law of cooling.
Here, how can you, this T naught will be related with this here using Newton's law of cooling? This is
Sir,
solid insulation, na? For solid, this conduction to solid material, this insulation is solid, some polymeric material. So from here to here, you will use Newton's law of cooling. That is what I am telling, that whatever we have covered in momentum transfer, that is also useful here in this case. Yeah, anybody else? Any idea?
Hello, sir.
Yeah, roll number 45. Prabodh.
Yes, sir. So we can write another shell momentum balance
Very
from
good.
R is equal to R and from to R AR.
Very good. So you are on correct path. But can you just spell out from where you got this idea?
So like I think in momentum balance we did a problem where there were two liquid layers and we did a
Very
separate
good.
momentum
Excellent.
balance for each
This
of them.
is this idea. You can take it from, we have two liquid layer flowing together, but they were immiscible with a different viscosity. So that there I explained that when a compound having different viscosity will behave like two phases in momentum transfer. Similarly, in heat transfer, if you have two material having different thermal conductivity, even though it is solid, this is also solid, this is also solid, but these are two phases for heat transfer because the heat thermal conductivity of this material and this material is different. So you need to write a shell balance equation for this phase where there is no heat generation. You need to write a shell balance equation for this phase where there is a heat generation. Here heat generation is 0. Heat generation is SE. So this is one phase and this is another phase, two phase problem. Now to get the temperature profile, how many boundary conditions are needed here? Prabhuddha? For two phase problem to get the temperature profile. So there will be one temperature profile which will be explaining temperature from R equals to 0 to R equals to R. There will be one flux profile which will be explaining from R equals to 0 to R equals to R. And there will be another equation, okay, for phase 2. This same equation is not true from here to here. Okay, so another equation will be there which will explain the temperature variation from R equals to R to R equals to AR, and flux profile from R equals to R to R equals to AR. And here this temperature is related with TN using Newton's law of cooling and heat transfer coefficient. Prabhuddha?
Yes, sir.
How many boundary conditions are needed?
So we'll need 4 boundary conditions.
So whether 4 boundary conditions are available here?
So we have one temperature boundary condition.
Yeah. So air temperature is given. This is one boundary condition. So this air temperature can be correlated with the surface temperature. Say for example, surface temperature is given. This is as good as surface temperature is given. This air temperature is given. So using Newton's law of cooling, so this is as good as surface temperature is given. So what are other 3 boundary conditions?
So I think, yeah, because in the last problem also we used a logical boundary conditions.
Yeah, logical boundary condition, because for this material, a temperature should be finite or flux should be finite at R equals to 0. That is another boundary condition. 2 boundary conditions. So how many boundary conditions are needed?
So 2 more.
2 more. What are these 2 more?
So one would be flux continuity. So flux in at the surface of
at this surface.
Yes, sir. Yes, sir.
At this interface between this insulating material and metal. So there will be continuity of the flux. Okay, continuity of the flux, and there will be continuity of the temperature. Okay.
Yes, sir.
At this surface, there will be continuity of the temperature also. Continuity of the flux and continuity of the temperature. You can call it as an insulation also. You can call it as a protective layer. So if you spell it as an insulation means it will stop the heat flow actually. Flux will be 0 here. That is not the case here. You call it as some protective layer. Not, it is electrical insulation. Okay, it is electrical insulation. This insulating material is for protection of a electrical energy, actually protective layer against the electric. So this is electrical insulation. Okay, so this is not the thermal conductivity is there. So if it is a thermally insulation, then thermal conductivity will have infinite value actually. So this, okay, this, so there will be continuity of temperature, continuity of flux will be there, and this air temperature is as good as can be correlated with the surface temperature. Thus now we have seen. So these are the 4 boundary conditions. You can solve this problem. Everybody got this problem? So I'm not going to solve this problem here. So this is the problem for you as a homework. Okay, homework, tutorial problem. You try to solve this problem, say within say next 5-10 minutes. And if you are getting any problem, any difficulty, any confusion, just let me know. Here roll number 46, Aishwarya.
Yes, sir.
Will you be able to solve this problem?
Trying.
Because 4 constant will be there and 4 boundary conditions are there.
Yes, sir.
Only you have seen that you got very complicated equation when we were discussing 2-layer flow. Here also mathematical complexity will be there. Fundamentally it is same. Okay, and here this air temperature will be related to a surface temperature using Newton's law of cooling. You can assume first T0 here. You can assume T0 here, and then T0 can be related with the air temperature. Exactly similar here what we have done. Na?
Yes,
So
sir.
you assume T0 and T0 equals to SER divided and not SER. So you need to calculate a flux at R equals to AR. R equals to AR. Similarly, you will get this flux at R equals to AR, and this temperature will be temperature profile for an insulating material, electrical insulating material. So using electrical insulating material, you will be getting this flux profile, and this will be flux at the surface of the electrical insulating material, and substituting this T0, initially assume T0, and then get the temperature profile and get overall and you will get a 4 equation as such. Here, there it is not a 2 equation only. Here, one temperature profile for this material, wire material, one temperature profile for insulating material, one temperature profile, one flux profile for wire material, and one flux profile for insulating material.
Excuse me, sir.
Yeah, roll number?
Sir, roll number 103.
103, Saurabh, tell me.
Sir, why can't we apply Fourier's law in the insulated section?
We will apply the Fourier law.
No, sir, we can, we have, let's say we assume the temperature on the inner surface of the wire is T naught, and the outside surface, the insulated surface is the T1 temperature. We can relate T as temperature to T1.
That is what you are doing. How this
Yeah.
so this is T I and
Yes,
this
sir.
is TW. How Ti and TW is related? It is related by Fourier law of heat conduction. There this Ki will come actually.
Okay, yeah, sir, okay, I got that. We were using shell momentum balance like that. I was thinking directly.
Directly, you can apply
No,
directly also. Only
yes,
that
sir.
one way is given actually. Systematic way
Yes,
to handle that equation actually.
yes, sir. Got it.
So here actually we are trying to analyze how shell balance heat transfer can be, shell balance is used in heat transfer. So anybody else has any doubt in this solving this problem? So this is the homework for you, and you try it out at home. If you are getting any problem, just I will wait for 5 more minutes and then we'll continue. We'll continue remaining part. Maybe we'll end early today. Only one problem is left. So you can solve this problem exactly similar way. Temperature is varying only in R direction. Okay. Temperature is not varying in L direction. Temperature is not varying in theta direction. Here only the thing is, so you have one phase up to R and another phase up from R equals to R to R equals to AR. So this is two phase problem. So for solving one phase problem, we need a two boundary condition. For solving one phase problem, one directional variation, 1D one phase problem, 1D variation, one phase problem, two boundary condition. So here I need a four boundary condition. So one boundary condition will be T air. This T air can be related with the surface temperature. That is one boundary condition. Another boundary condition is logical boundary condition. At R equals to 0, my properties cannot be undefined. And two boundary condition will be at this interface. There will be continuity of temperature and continuity of flux. So you can get a temperature profile as well as flux profile in this insulation and a wire material. Everybody can solve this problem. Please got the idea to how to solve the problem. Anybody has any confusion? Yeah, roll number 48, Hansraj.
Yes, sir.
So shall we move on?
Okay. Yes, sir.
Okay, okay, now you can solve the problem.
Yes, sir. Solving, sir. Yes, I am getting, sir.
You are getting na, at least idea.
Yes.
Only complexity is there in mathematics. And certain, I will tell 100 times that handling mathematics I am not going to cover in a class. Here we are not going to cover how to handle complex mathematics. Just I will give the idea. Okay, take down this problem and solve this. Very easy problem. A copper wire has a radius of 2 mm and a length of 5 meter. For a voltage drop, what voltage drop would temperature rise at the wire axis will be 10 degrees Celsius if surface temperature of wire is 20 degrees Celsius. So for copper, Lorentz number at 20 degrees Celsius is 2.23 into 10 raised to minus 8 volt square plus Kelvin divided by Kelvin square. So here, what is the temperature at the axis? Hansaraj? Roll number 48. Roll number 48. Roll number 48, Hansaraj. छोड़ के चला गया क्लास. Roll number 49, Harshvardhan.
Yes, sir.
Oh, Hansaraj is gone. हाँ हर्षवर्धन बोलो एक्सियल टेम्परेचर कितना है?
Sir, I'm solving, sir.
एक्सियल टेम्परेचर कितना लोगे? वही तो बोल रहा हूं मैं. What is the temperature at the axis?
So that we'll find using the temperature profile.
Here it is given, surface temperature is given, axial temperature is given, you need to estimate the voltage drop, and voltage drop is related with the heat generated per unit volume. Okay, heat generated per unit volume, and this Lorentz number is given, Lorentz number. So we have
30 degrees Celsius.
Heat generated per unit volume is related with the current density and potential difference. Current density and it is related with the potential difference. There you need to get the value of potential difference. Voltage delta E. So that E need to estimate for the temperature, surface temperature 25 degrees Celsius and axial temperature is Harshvardhan, what is the maximum temperature?
So we will find that using T max minus T naught is SC R square by 4K.
Yeah, what will be T max minus T naught?
Sir, I'm calculating. T max minus T naught will be 10 degrees Celsius.
Yeah, T max minus T naught is 10 degrees Celsius. So maximum temperature is 30 degrees Celsius. Surface temperature is 20 degrees Celsius. So T max minus T naught is 10 degrees Celsius. So R equals to 2 centimeter. Length equals to 5 meter. Where the length is given, length equals to, yeah, tell me.
Sir, you were not audible for last 2 minutes. I guess there was some network issue from our side.
हाँ प्रतीश
Sir, you were not audible from last 2 minutes. Last thing we heard was T max minus T naught is SE square minus upon 4.
Yeah, I was quiet actually. I was just waiting for you to solve the problem. I was
Okay,
not
okay.
talking anything.
We thought there was some network.
Not network problem.
Okay, sir.
Time was given for you to solve the problem.
Yes, sir, great.
Anyway, that Harshvardhan has told how to solve the problem. So this R is 2 centimeter, radius is 2 millimeter, not centimeter, 2 mm, length is 5 meter, T naught is 20 degrees Celsius, and T max minus T naught is 10 degrees Celsius. This you can say rise at the axis is 10 degrees Celsius. So initially the wire will be at 20 degrees Celsius. So rise is 10 degrees Celsius means T max will be 30 degrees Celsius. T max minus T naught is 10 degrees Celsius. So T max minus T naught is SE R square divided by 4K. Again, this SE is related with the current density and electrical conductivity. And this electrical this is related. You can incorporate Lorentz number. This current intensity is related with the electrical conductivity, potential difference, and R. So you can substitute it here, rearrange the equation. You can substitute it here, rearrange the equation. Okay, rearrange the equation. So you can see. So potential difference will be equals to 2L. L is the length divided by R is under root of K minus KE into T naught. T naught. So this is Lorentz number. This is Lorentz number multiplied by under root of T naught minus T max minus T naught. So T naught is 20 degrees Celsius. Okay. So 20 degree Kelvin, you can write in Kelvin actually. So this
Excuse me, sir.
Tell me.
Yes, sir, I added out. So it was given that the temperature at the surface is 20 degrees Celsius and at the axis there is a rise of 10 degrees Celsius. So are we considering means that the temperature of whole wire is at same?
No.
Will the temperature at axis and surface will not vary?
It will vary, no? What you are telling?
So in the question means it is given that the temperature at the surface is 20 degrees Celsius.
Look, initially assume that there is no current flowing. So whole wire is at 20 degrees Celsius. Okay? And outside surface temperature is maintained at 20 degrees Celsius.
Okay, means that's the normal temperature of without any electricity, no heating.
Without any electricity, but surface temperature, not air temperature, surface temperature is maintained at 20 degrees Celsius. Okay. Now current is flowing. So there is a rise of 10 degrees Celsius at the axis.
Yes, so it was not clearly given that there it was maintained. So we thought that there might be initially some current.
This is maintained. Outer surface is maintained at 20 degrees Celsius. T naught, you can say T naught, you can take it as a 20 degrees Celsius. So there is no other way to assume and solve the problem. No? What is this 20 degrees Celsius then? So anyway, transient problem solving still we are not into. You might have solved in heat transfer some of the cases, but here in transport phenomena you are not into transient problem solving actually. We will consider only steady state. So at steady state, wire temperature is given, surface temperature is given 20 degrees Celsius, actual temperature is 10 degree rise at steady state. So
yes,
after 30 degrees Celsius, it is not rising again.
So means next time also we need to consider that initially there will be no current flowing and we are comparing with that state, right?
No, this is not initial. No? Outer surface is maintained at 20 degrees Celsius.
Okay.
Initially, everything, if you maintain outer surface as 20 degrees Celsius, everything will be at 20 degrees Celsius, isn't it?
Yes, sir. So will it be mentioned, or we need to understand that it will be maintained
Yeah, you
in
need
whole
to
wire?
take the information from the problem actually. That is what writing a given data is very, very important. You write this 2 mm, this is R, no confusion. You write this 5 meter L, no problem. You write 20 degrees Celsius. So what is 20 degrees Celsius? Surface temperature. So this is steady state temperature. Steady state surface temperature is given 20 degrees Celsius. Surface temperature, T0 is given. And actual
sir,
one is 10 degrees Celsius. So this is T max minus T0. Okay. Got it? So
Yes, I got it. Thank you.
what is potential difference? Yeah, roll number 49. Harshvardhan.
Yes, sir.
कितना है?
Sir, 40 volts.
40 volts. So substituting this, it is 40 volts. Okay. So we'll continue our discussion in next class.